Yeah.
Yes, please. That would be great.
Hello,
Thank you,
some people. Can you hear us? Can you hear us, Shilin? Hello, hello. This is a test. 1, 2, 3. Can you hear me?
That's good. That's good.
Hearing.
Oh, careful with the feedback.
Okay.
Wait 1 second. How do I? Oops.
So it's being recorded now.
But I have audio in my computer, which I do not want to.
Okay, I don't hear the feedback anymore. So I guess
Oh,
we're good.
because I had it on.
Oh, okay, it was there. I think we're good.
It's true.
Some people, can you confirm that you hear us?
I guess it's just us right now. Okay.
Frederick was going to join us. Hello, hello.
Did you join the meeting over there too? Or is this my, because I just turned the speaker out.
So if you can hear you, I'm sure.
Yes, okay, I can hear us.
So do you want to introduce?
We can, yes, of course. So we can start. Okay. Well, let's go for it, everybody. Hello, welcome. Thank you very much for coming today. It is my fantastic pleasure to introduce our speaker today, Edgard Bonilla. He is has been my best friend since undergrad. We have known each other since 2009, and I'm going to steal your screen for a second just to share an embarrassing picture. Here you can see us. This picture was taken in 2010, right after we finished our first year of college. That was with the crew. We were taking the math honors course. That's where we met. And he was insufferable, and I was very silly. But we became friends, and both of us did character development. So I'm very happy about that, and I'm very happy to share him with you today. Anyways, he did his undergrad in Universidad Simón Bolívar in Caracas, Venezuela, the same place as I did. And he came to the US to do his PhD at Stanford University with the LIGO collaboration group in 2015. And he has been working with them in basically every possible thing you can imagine. He's an extremely flexible character. I don't know how to describe it. You're an experimentalist, an instrumentalist, a theorist. Yes?
I like to say I'm the theoretical instrumentalist.
Yeah. So he has worked in a lot of stuff that I'm not going to bore you with details today, but if you schedule a time to meet with him, you can ask him about his interest in instrumental and experimental work. Today, he's going to talk to us about approximating operators for reduced order model, which is his night job when he collaborates with us on theoretical nuclear physics. And the final thing that I'm going to say, and then I'm going to hand it to Edgar, is that after his seminar, we're going to go for lunch at the cafeteria. Anybody that wants to join us, you're welcome. It will be very nice, and we can have informal talks. I think that is all. And with that, I leave it to you, Edgar.
So do you want to say for how long Edgar is staying?
I'll be staying here until Wednesday, technically, but I don't expect to be coming here on Wednesday because I need to prepare some stuff because immediately after this, I'm going to MIT. We're going to be having a workshop to design the new LIGO suspensions, and I really need to be there. So yeah, so it's going to be today and tomorrow if people want to talk with me, and I'm just going to be around. Yeah. Okay, so thank you, Pablo, for the wonderful introduction and for the embarrassing picture that I did not know you had. Anyways, as Pablo said, I'm just going to talk a little bit about the work that we've been trying to do together with reduced order models, and I hope to, bring a little bit of extra perspective, a different point of view than the one that Pablo usually presents, and maybe Kyle as well, and see if that can get some interesting conversations going. So the talk, I'm going to try to keep it relatively short because in the LIGO collaboration, as I was telling someone earlier, people really dislike talks that go over 20 minutes. So I try to make it a little bit longer so it fills the space, but no promises on that. Anyway, so just this short outline. I'm going to try to motivate why we want reduced order models, which you probably already know. Anyways, and talk about a little bit of preliminary ideas from math, and then jump directly into operator approximation. And finally, just show a few of the preliminary results we have with reduced order models in the work we're all doing together that I'm a part of. So yeah. Anyway, so just to motivate the use of reduced order models, I'm going to talk about two examples that I'm sure you're very familiar with. And I'm not expert in Euclid physics, but I find some of these things very, very exciting. One of them is the use of optical potentials, which are used to understand some aspects of reactions of nuclei. And in principle, you could use this information to kind of model this blue curve over here, which I find particularly as a LIGO scientist very exciting, which has to do with the synthesis of nuclei in neutron stars. And the problem with making those types of calculations is that usually each one tiny square on this grid is a different nucleus and different isotope, and you would have to be able to understand the abundance of elements on in the universe. You need to perform a calculation that goes up that ladder, and for that you need to be able to model each particular nucleus and perform repeated calculations for that. Another interesting thing that I think we've been working pretty hard lately, both Kyle, Pablo, and I, is density functional theory, which is, I'm told that it's a theory just to try to understand the structure of nuclear matter in a mean field way, and try to use that to get some sets of limits of what is the properties of the nucleus, and maybe when you cannot accept any more neutrons and the isotope is just not viable anymore. And again, it's part of the calculations that people use for nucleosynthesis and for estimating the abundance of particular nuclei for formation in neutron stars. This is interesting stuff, and I'm not gonna try to spend much time in this, but the way I like to think about it, which is a very abstract schematic way, and this is going to be a very schematic presentation in case you're not noticing because of how bare this slide is. The way I like to think about it is that usually the type of problems that we're trying to solve are contain a physical model that's coupling together some interaction parameters, couplings between different nuclei, between different particles and forces, and so on and so forth. And we want to somehow go from that physical model to some observables, quantities of interest, stuff that you could see at the lab or at the observatory or at the telescope, or something that LIGO could say something about. The thing is, usually those physical models for nuclear physics look like something like this, which is, at least to me, something extremely complicated. And the number of parameters that we're talking about is massive, even though they're constrained by a few nuclear matter properties. It still means that whenever you have to search the parameter space to do any systematic studies of nuclei or to do any uncertainty quantification, you need to be varying everything at the same time and perform a calculation that starts stacking up and becoming expensive if you really want to do the science you want to do. So again, inside the schematic, you could replace that physical model box by an actual model like this DFT model over here. And you can imagine that doing the repeated computation, you just become burdened by the computational cost of doing science. And that's a reason why we need surrogate models. And a surrogate model in this case is some way of abstracting this box and making it a little bit more simple so that we can get more quickly from our interaction parameters from our theoretical variables to the observational ones that we can see at the lab. So that's how I generally tend to see it, and it's an easy workbench, at least for me, to think about stuff. Now, how do we get to the surrogate models? And before that, I'm gonna maybe jump to a little bit of math. So I'm just going to talk about some preliminary ideas that are going to build up to reduce order model stuff. And please feel free to stop me at any point on this part, because the second part of the talk is going to heavily rely on whatever I say here. So the first thing that I really like telling people is that we really need to be thinking about functions as vectors. Usually we're used to thinking of functions as this little box that is just mapping some numbers to a different space, and usually just represent them as a graph. So you just take an X, you put it onto the function, and you get something that looks kind of like this. And in this particular case, I'm joking, I'm putting a damped harmonic oscillator because that's all I can think about lately, given the work that I'm doing with designing suspensions with LIGO. But a way that I think is very productive in terms of approximation to think about functions is to think about them as a set of points, like a list of points. And it's very more similar to how it actually would be represented in a computer. And of course, once you're thinking about them in that way, it's very natural to start thinking about the points of the function, the values themselves as coordinates, and this as basic, oh, look, spoilers, and this as basis vectors. So in principle, you could think about a function as a linear combination of many coordinates that are all together that represent the values of the function. And again, in reality, you would need infinitely many of these points to be able to represent the function, and it becomes a little muddy and complicated. But some mathematicians in the 50s made the whole generalized function theory, and that's what we lean on. And we're physicists, so we can start abusing the notation and thinking about the functions as tiny arrows in infinite dimensional space, right? So in the same way that we're talking before, thinking about a couple of points, you can imagine using abstraction that each particular function is just a point, a tiny arrow in an infinite dimensional space, and as the function moves, the tiny arrow moves around and just describes different functions in the abstract space. And of course, in this particular visualization, we only have 3 dimensions because, well, sadly, I cannot render more than that in a reliable way that anyone can understand, or at least not one that I can understand. And in this particular case, just so that you get a sense of what's going on, the 3 red points are the 3 coordinates that I'm actually plotting on the right-hand side over here. And this is just similar to changing the natural frequency of a harmonic oscillator situation. And as you change that, the function that describes your system is moving on that abstract dimensional space. Okay, so that's the first thing. And why is this powerful? Well, of course, once you're thinking of functions as vectors, you can start asking yourself questions that are more normal in linear algebra, like what happens if you change bases? Can you represent functions in a more easy way? Is there a way to represent all the coordinates in a more compact way, et cetera, et cetera? And that will lead onto the dimensionality reduction stuff that we're going to talk about later. Any questions up to here? Okay, cool. Second thing, another interesting thing that I like to talk about a lot is that usually we define functions are used to defining functions in a very explicit way, where you just tell me phi of x equals some function of x, where you just plug and play to obtain the coordinates of the function. Remember, we're thinking about functions as vectors, so every time I say phi of x, I'm not thinking about the plot of the function, but rather the coordinates that represent it, and just plug x to get coordinates. However, there are other ways to describe functions that are equivalent, completely equivalent to that. This would be like an implicit definition, which is a differential equation. This is describing the exact same coordinates, the exact same point of that abstract function space. It's just written in a completely different way. And you would think about it as an equation, but in reality, it's just a definition of the same function. And the definition is trying to relate the coordinates themselves in some way. And this is not very different from saying, hey, instead of giving you the equation y as a function of x for a circle, I'm just going to tell you, hey, a circle is a set of points that has the same distance to a center. It's the same definition. I'm describing the same thing. It's just written in a different mathematical way. All right. So this is I made a tiny typo over there, but if you don't believe me, if you're still not convinced about the the thing about the implicit definitions, you can imagine discretizing that equation and really thinking about those tiny points. And each one of the equations is actually implicitly telling you something about the equation. So, about the function. So this first equation is telling you about the first point. The next one you can use to relate the first two that you have now. The next one you can use to get the third one, and so on and so forth. You start propagating and getting all the way around. In this sense, when we're talking about functions as vectors and implicit definitions, the function phi, or the vector phi, if you want, in this abstract space, is just the root of a vector operator. So this function f, which is a bigger function that just eats vectors and spits out vectors, has a vector root at the particular function that it's trying to define. All right, so good. So that's enough math for now. Any questions here? Because this is the point. This is the point where I jump out from this.
That was not a question.
It's not a question, Paulo. Okay, good. Fantastic. All right, so I have a question for you. Why do we care about this? I mean, we're doing physics. Like, yeah, sure, abstract vectors in space, whatever. Edgar, what are you doing? So the reason I think we might care is because once we're thinking about it that way, when we have our physical model of interest, we can just abstract it completely and say, hey, the functions, the wave functions that describe our particular nuclear systems are part of a vector space. And what we're trying to model is the equations themselves that capture the properties that those functions are defined by. So one thing I want to invite you to think about, which is maybe a little bit different from what we thought about reduced order modeling before, instead of thinking about approximating the functions that are the solutions to the equations, what we're trying to do with reduced modeling is try to capture the properties of the equations themselves that define the functions. And I think one of the things I like about this framework is that it ties together many ideas from different fields. It's very easy to think about the box or the equations themselves as a thing to approximate when you're thinking about something like neural networks or autoencoders or reduced basis methods and so on and so forth. What you're trying to do is somehow get at the map that is in the box instead of the specific functions that you have inside. And the way that you approach this with different methods is a matter of philosophy, and they all carry some trade-off between the ability to be accurate and reproduce all the physics that we want and the computational speed that we're going to obtain by using them. All right, so now one thing that I'm going to talk about is the reduced basis method, because that's where most of our work has been going on, and I think I'll just try to frame it a little bit closer to this slide and see where we get. And the first thing is, if we're going to talk about the reduced basis method, instead of thinking about approximating the functions, what it does is just project whatever your equations are onto a low dimensional subspace that has to do with solutions of your equations with other roots of your equations. And one step further is it uses the singular value decomposition to try to get at the important parts of the equation that more closely resemble what we care about in the physics, which are the roots of that equation, which represent the states that we care about. And in principle, again, in the vector picture that I was talking about before, this is the same as saying, hey, I'm not going to want to use this coordinate space where we look at each particular value of the function at any coordinate space location, but rather change for a different coordinate system where we look at a global type basis where you have a function and we just put in different weights on them. And these new coordinates, in some sense, are equivalent to the previous ones. It's just a different way of representing the same vector. It's like changing from, Cartesian coordinates to some polar coordinates, or changing or rotating your system. It's not anything particular from the mathematical point of view, but it can carry a big change, or it can have a big impact on the way that you calculate stuff when you are using to approximate the operators themselves. So in the particular case of differential equation, this one here is just a quantum harmonic oscillator because it's just easy to write. And if you were to use a coordinate space representation, and I am aware that this is not a quantum harmonic oscillator wave function, you would need thousands of equations to get a good enough representation of your operator and represent the root or the wave function, the ground state that you might want to represent. But if you go to a reduced basis, you might only need just 2 equations to get most of the information that you need because you used a convenient basis change. And so you change your operator, your equations themselves from 1,000, an object of dimension 1,000 by 1,000 by something that's 2 by 2. And just another visual, because I really like visualizations as a way to convey math, this is what happens if you try to emulate the ground state of this harmonic oscillator in the reduced basis. And you can see that by very, very little small change of only 2 coordinates is enough to more or less reproduce your function. And that's what generally we would want. It's, of course, it becomes more complicated the more complicated the model is. And for something nonlinear like DFT models or things where you have level crossings and you only have discrete amounts of levels that contribute to the ground energy of the system and it iterates, it becomes challenging to do something so simple. But this is at least the premise of the method. Okay. How am I doing in time? Good enough. Right. So it's very pretty. One caveat, and I think is very important to remember, and I think it will definitely come out later in the presentation, is that this type of method, like the reduced basis method or any surrogate model, in the picture where we try to reproduce the equations, the operators themselves, is only effective if the equations that you're using, the surrogate model itself, is simple. If you're not able to extract that wave function out of this reduced model, the surrogate model, then the approximation might be very good, but computationally speaking, you're not going to get any efficiency. And so that's the goal. So the goal is every time that we're trying to do a surrogate model is just get equations that are really, really easy to solve, or at least easier than any other way of extracting that information. Okay. And once again, it bears repeating, any approximate method is always trading accuracy for speed. So there's no free lunch, except if you're maybe an inside trader in Wall Street, in which case there is a lot of free lunch. But we're physicists, so we don't have free lunch, sadly. We abide by the rules of nature. Anyway, so there's one case of interest that will happen, and it will make it so that you really cannot extract that information so effectively, which are what people in the business call non-affine potentials. And this is the most math-heavy slide of this whole presentation, and I apologize in advance for it. But there's many cases where each one of these equations that we want to solve, which are these projection equations in the reduced basis method, they just cannot be factored in an easy way. So this particular example, you can talk about this projection operator. This projection is just an integral over the whole space that you're interested in. And if you have a potential, in this particular case, this is a two-body scattering interaction. And if your potential U that will appear in this integral is written in a particular convenient way, such that whenever you have the parameters that you're dialing, that you're using to track your solutions, comes out of this integral in what's called an affine type representation, this whole integral over here does not depend on the particular parameters that you're trying to change around as you're exploring your space of parameters for uncertainty quantification or for any type of study that you're trying to do. And so you can pre-compute that integral, and the equations that come out of it are simple equations, are equations that will be linear or, at most a simple polynomial in the new coordinates of your vector. However, if it's not like that, for example, in this case, this alpha parameter is right here inside the exponential, you cannot pre-compute all these integrals at from the get-go. And then even though your approximate equation is very good, in principle, if you could solve it, you would get a very accurate representation of your space or of your vector, and of course of your nuclear system. You cannot do it efficiently, and if you cannot do it efficiently, then why are we doing this? So there's many ways to deal with this, and in the reduced basis method, go ahead.
Just want to understand the difference between nonlinear and non-affine.
Yes. Oh, I can explain. So the reason here is the real terms should be nonlinear. And I can understand where you're probably coming from, which is this this idea here that alpha is inside that integral in a way that you cannot be factored. But you can imagine, for example, that this alpha over there is an alpha squared. It will still be nonlinear, but it can still be factored out of the equation. So it's linear in a linear in a different sense, in the sense of like you can factor out some of the coefficients of the equation. Now, people tend to use the term non-affine instead of nonlinear because we reserve the term nonlinear for nonlinear on the coordinates of the approximation. It's just as a matter of separating the two terms and keeping the discussion a little bit more clean. If that makes sense. Does that answer sufficiently? Thank you.
Why don't you just say separate or non-separate?
Maybe that's a better term. It seems to be, yeah.
So it's nice.
Yeah, that's right.
Just not
I was just going to say it seems to be a historical thing that people like to say affine because everything that can be separated in a linear combination is technically affine. So mathematicians like their fancy words, and I think that's good.
Hey everybody, this is Frederick. I don't know if you can hear me there.
Yes, I can hear you.
Yeah, I couldn't hear the suggestions from the room, but I think the correct term that you're looking for instead of affine is that U has a tensor product structure plus a constant term. Tensor product meaning it's a product of two functions. One of them depends only on alpha and the other one depends only on R.
That is correct.
And that would do it. Yeah, tensor product.
Yeah, that's correct. Yeah, but again, I think going back to Vitek's suggestion, you could say in a more simple, more plain language, you could say separable, and that probably still does the trick.
That means the same thing. Yeah.
Yeah. Suggestions? Go ahead. Sorry.
Do you consider functions which allow relations or relations to prevent? So suppose you have like the atomic and the physics atomic constants.
Mm-hmm.
That allows you to set up the Gaussian relations to allow you to use the
Right. Right.
That's what's the base. But then you chose the basic size and
That's right. Yeah. No, and that's a completely viable strategy too. It's just find a different representation for the functions in a way that allows you to pre-compute these integrals. And in fact, that brings me exactly to the next point, which is that usually what people do is what's called empirical interpolation, which is essentially take those operators and try to write them as linear combinations of other things that are easy to handle so that you can pre-compute those integrals. So again, it's exactly as you're suggesting, you just take your function that is complicated and try to write it in a separable way so that you have a part that only depends on the coefficients alpha and another part that only depends on your variable that you're going to integrate over so that you can simplify all your equations and only deal with the different dependencies separately. And the way that it's done, again, this is a little bit detailed, and I'll be more than happy to discuss offline, but I want to keep it simple in the slides. You just project your function into some principal components or some function space of interest that we think is good enough to approximate what's going on, and then somehow interpolate or get those coefficients B of alpha that will track the function as we tune the parameters. And the way that it's done in general in the reduced basis literature is by using interpolation, which is just essentially saying we'll try to make that approximation exact at some specific points, and then everywhere else we just kind of hope that it works, that it just falls into place. And there's a little bit of detail, subtlety that goes into it. The point selection. Go ahead.
Does your FR should have an index? The first page.
That is correct. It should have an index I. Yeah, that's excellent point. So Shilling was mentioning that in this particular slide, these Fs are supposed to have an index I, and I did miss that, and they're just a singular F. So thank you. Good clarification. All right. So in this particular case, you just want to choose points carefully in such a way that you can reproduce the function the best you can. And this actually gets into a lot of interesting stuff that I do not have time to talk about. Pseudo-skeletal approximations, maximum volume, submatrices, optimality, experimental design, blah, blah, blah. It's pretty cool. And it is important to recover a good model of your potentials in case they're non-affine. Go ahead.
I have a question about careful,
Yes.
because this suggests that there is some neutrality.
Yes.
That when we go on application, we make some choices.
Yes.
And somebody else will make choices.
That is right.
There will be different results. Cannot formalize it better.
Right. Right. This is an excellent question, and it's one of the things that I personally also. I'm not sure if I'm talking too much for you by saying I also dislike about this type of method. I am not a huge fan of fine tuning things just to you get a better result, because you cannot formalize things and you cannot make it reproducible for everyone. Sadly, at this point in time, I will tell you that the way that this is done is completely empirical. You just choose some points in a way that you think makes sense, and then kind of hope for the best. And it's a little bit. I don't like it particularly, but I think it's the best we have up to now.
Don't choose by hand. No.
And this is exactly, Kyle says an excellent point. We don't choose it by hand though. What we tend to do is, just to try to make it reproducible, is to grab the principal components, which are well-defined for a particular operator and a particular range of parameters, and then grab the points as the points that maximize the how do you say that have the best condition number for approximating your operator, which is essentially just grabbing a maximum volume or maximum information set of points to interpolate your function. Yes.
Principle. Based on your primary basis,
Mm-hmm.
as in your first figure, right? You get your vector stuff.
Mm-hmm.
And then based on this choice, you do it.
That's right.
And then you get your full picture. But you get this first step,
Mm-hmm.
which is not good under the.
Right. But yeah, and let me.
After the first step. Well, you get
Sample the parameter
a
space.
sample parameter.
Okay.
Okay.
You sample parameter space, use that to get SVD, and that's the same for these operators. You have to sample parameter space, and that step is problem dependent.
Right.
Yeah. Right. Right. That is correct. That is also viable. And it's the thing that people have done too. Yeah. Sorry, could you do the source? What? Excuse me. So it depends on the problem, and I do not know exactly what the results would be for the reduced basis method. I know that people use autoencoders just from the get-go at the higher picture, at the highest level. most people that try to use autoencoders to try to solve partial differential equations, they just do it on the equation as a whole, not on a subset of it. And the results are actually quite good. Of course, it depends on the equation, and a lot of the results that you get to see out there in the literature tend to be for either toy models or simplified things. But even some of the simplified things are simplified things in fluid dynamics, which involve like 3D type simulations. So part of me wants to say, it's still a nascent field, but some other part of me says, wow, this is very impressive, actually. And because I'm not part of the field, I have a hard time judging exactly the quality of the results. I think that's the most scientific answer I can give you. But yeah, okay. So there's some arbitrariness on this, and I think that is one of the things that I personally dislike about this. But in all seriousness, you can still find some ways of how do you say that, assess the quality of your results if you have some standard model. Wow, awful selection of words, but just some how do you say that, some like a particular very high fidelity calculation that you can use to contrast your results with, and that way report your approximation error in a way that at least makes sense, and you can say, hey, this is what we did, and this is the approximation error that at least statistically we expect to have. Okay. Excellent discussion, and that's exactly why I like leaving everything schematic. It leads to a lot of discussion, which is really good. Okay, so just presenting one result from the people working on ROSE and from the band collaboration. This is something that has been done already and has been implemented in the package, just using empirical interpolation to approximate both the real and imaginary parts of an optical potential. And you can see, at least visually, it's not quantitative, that the approximation is really, really good. Just with about 10 bases or 10 principal components, you can reproduce most of the potential very, very well. All right, so going back again into the whole, we're approximating operators, I don't want you to forget that this potential that we're approximating is actually a matrix. This is a diagonal matrix in this particular case, which we're just approximating the diagonal. It's not just a function that we're trying to approximate. And then, no, it's not that we needed 10 principal components. We use 10 principal components.
But I guess
That's correct.
That's not correct. Because the radius, the problem is variables like the radius that move the thing a lot. You need a lot of things to track that down. So I can show you the details later, but 14 bases seems to be working like really good, and the speed is perfect. So
yeah, I'm about to show a trade-off for speed for this particular case, and you'll see it's, even though there might be some loss, it's very little in terms of speed. Yeah. Anyway, so yeah, it's an operator. We're approximating a diagonal matrix, which lends itself very well to another of the problems that people have been talking about a lot, which is what happens if we have no local potentials in the space representation. This is just like having a non-diagonal matrix, and all the methods that I said before still work. There's no particular difference between a diagonal and a non-diagonal matrix in terms of just approximating as a basis of things. And we've tried this already, and it seems to have promising results, but no particular pretty plots to show you more than the schematic for now. The last thing, and this is what we've been, how do you say that, throwing a lot of our effort and hours on. Suffering. Yeah, suffering, that's exactly right. And a lot of long phone conversations with Pablo basically all the time, is what happens if you have nonlinear structures. And what I'm referring by this is situations, for example, in DFT, where you have terms in the Hamiltonian or terms on your equation that depend on the density to some power. And the density here, again, is a function, is already a nonlinear function of the coordinates that that are vector, the vector we're trying to approximate. And all the equation will have a tangled mess of functions trying to interact with one another. And it's very hard to extract the coordinates that would give a root to our system, or better said, the eigenfunction of our system. And it's very, very complicated. And this schematic here is our humble attempt at trying to simplify what we're trying to do to make it simpler. And in this particular case, it involves trying to address some bottlenecks on the calculation by simplifying some particular structures that repeat themselves in the equations to get a better operator approximation. But it starts becoming a lot of fine-tuning, a lot of doing things ad hoc, a lot of just trying things until something works, which is, again, not ideal, and it's not the type of very cool, smooth sailing for reproducible stuff that you would generally want. But it's a start. And the idea is that maybe once we start getting some rules of thumb of how to do things better, with a good ability to assess our accuracy losses by doing every approximation along the way, then maybe we can get some results that are actually reproducible and good science. On that note, I want to remind everyone, and this is what, the third, fourth time that I've said this already, each approximation, each step, each part of the operator that you try to approximate again by a different, a simplified, or a surrogate model represents a trade-off between accuracy and speed. So we're doing those approximations because we're forced to, so that we can get the faster computation to get to the physics we want. And especially when working with the nonlinear structures, it's really easy to start to lose sight of what the trade-off is. So one of the things we've been using, and I think it's one of the things I'm the most excited to show you, is a way to visualize the trade-off that we've come up with to try to get a sense and not fool ourselves into thinking that we're making progress when we're not, which is a computational accuracy time plot, which is called a cat plot because we really like cats apparently. The idea is for a particular problem and a particular method of calculating the coefficients of your of the functions or the wave functions of your system, you can plot the computational cost, the computational time versus the approximation error of some particular metric. So some particular observable or something that we think might give an indication of how good our approximation is. And in principle, in one of these, the trade-offs should be visualized something like that when you have a method of calculation. And as you increase the complexity, as you go to more complex models, you should have a gain in accuracy, so the errors should drop. But at the same time, you incur computational costs, right? There's no free lunch. And ideally, when we have better emulations or better ways of calculating stuff, then you should have a different method that is categorically different from the first one. So there's no point, again, in comparing something on the very high-end computational time, very low approximation error method one, with something that is in the low end of computational effort and really, really bad accuracy in method two. It's better to try to compare the two of them as a whole in order to know what you're getting, know what you're actually improving when you're searching for better ways of calculating stuff. And another thing that I think is very useful, at least personally for this type of plot, and I'm about to show you some examples in a little bit, is that you can also set some target performances, right? Like if you want to do some uncertain quantification or some systematic studies or something like that, you probably have a target accuracy that you say, hey, there's no point of approximating any nuclear energies to the EV level. We really don't think we need that level of accuracy. You can say anything below this line is good enough. And if you want to do some studies and you have some budget time, say a week to do the calculations, we don't want more computational speed than that. If you can click on a computer and make all the computations in a second, it's great. It's a great way to flex, but do we actually need it? Right, so this is a lot of the conversations we've been having lately, and I think I'm obsessed with trade-offs lately because of LIGO work again. Anyway, so two caveats, and I think Kyle specifically will make sure I point this out. All of these plots will be problem dependent. They cannot compare two emulation techniques or two calculation techniques in the abstract, it will depend on the problem that you're trying to do. It depends on the approximation error that you're trying to achieve. It depends on the software implementation that you're using. If you're using compiled language versus a non-compiled one, there's a lot of stuff, but still it can serve as a starting point to try to compare different methods and kind of level the playing field and say, hey, if we're using reduced order models, if we're using a coarse grain model, if we're using something like a Gaussian process, et cetera, like what are we getting? What is the trade-off? All right, so finally, examples. This is a calculation that we did by using the current implementation of ROSE. This is for an optical potential for calcium 40. And the two bounds over here for Bayesian uncertainty quantification are based on, wanting to have about 100,000 samples per hour, something like that. And we want some error on the differential cross section, at least relative error, to be of the order of 10% or so, maybe a little bit under 10%. And as you can see, there's two methods in here that are being compared, and each point represents a particular calculation. So I don't want to show you just averages, just so you can see the actual variability on the results. And one of them is a Runge-Kutta. I hope that's how it's pronounced in English, right? Solver with varying accuracy parameter. And then the other side is the reduced basis method using empirical interpolation in the Bonilla way that the ROSE package is doing it. As you can see, it's already hitting the target for uncertainty quantification. And in fact, I think they showed some cool results on a meeting like a month or so ago. Is that right? Yeah, months are passing, so I'm flying by. But
those two things only make sense.
That is correct. So in this particular case, if I'm not mistaken, the lowest end is something like 14 bases or something like that.
It was 14 bases for the wave functions and 14 for
That's
the
right.
for the good saxons.
14.
14 is the high end.
Yeah,
and
it's the high end.
4 for the wave functions and 14 for the optical potential is the upper end.
Yeah. So that's right, and that's one of, again, it's one of the.
So we couldn't change a step size. It's a initial value problem solver. What we could change is the tolerance. So we are changing the tolerance from 10 to the minus 12, the high end, to 10 to the minus 3 on the upper end.
Yeah. Thank you, Paulo.
20 minutes is one of the results we present in the band meeting. One of the calibrations.
Yeah.
And we choose a scattering cross section at 58 theta equals 50 angle 50 degrees, just to show something.
Yeah. Thank you, Paulo. That's a little technical. It's very good. Yeah, and again, similar example, but very different problem. This is what we've been working on for the last couple of months for SCRM DFT, calcium 48 in this particular case. And you can see that the blobs of uncertainty for many different parameters, these are little tweaks of how many bases we're using, how many things, how we're approximating things, they're actually not that separate. So if you have, even with a very coarse grid size or something like like 100 points or something, you can still get reasonable results with the final element that are not very different from the ones that you would obtain with the reduced basis method. And we're using Mathematica, and that's, yes, that is correct. That is correct.
Shift to the left, or they could do separate things.
Yeah.
So
both results are using Mathematica. Both are using Mathematica, and right. So this plot only makes sense if at least you're trying to use the same hardware in both plots, and otherwise it will be a really unfair comparison. We're already, we're already kind of stretching the amount of information we can show in a plot, and making many things move very different will make it for an unfair comparison. And it will be harder for us to design what we're trying to do. And again, this is work in progress. Everything is in Mathematica, so you would imagine that all of these results will shift to the left as we move first to Python or better to a Fortran type implementation that would be faster. And there's no guarantee that the RBM and the final element will scale the same when you change that software implementation. In fact, I think Kyle has made some preliminary results for the reduced basis method in Fortran that show that are promising in terms of knocking that down a couple orders of magnitude. But we're still not there yet, because the idea of the workflow that we've been having for this type of things is Mathematica is a really easy place to start trying different things first and see and how do you say that is try to compare different emulator topologies before going to the actual implementation in Fortran, which would take a little bit more effort to set up. If we're constantly having to change the way that we're emulating different boxes, it would take forever. Yeah. So, right. So surprisingly, I actually took more than 40 minutes. My advisor would be really mad. No, but it's a great conversation. So, all right. So I'm just gonna try to keep it brief with the takeaways. So, in the abstract side of things, functions are vectors. I think that's one of the things that I really like to say a lot of the time. Is just a function is just a tiny point in the abstract infinite dimensional space. Emulators, it might be helpful sometimes to think about them as a way to approximate the operators on vectors or approximate equations themselves, not solutions to those equations. The second thing is that is a little bit closer to the actual implementation. The first one is that low dimensional manifolds sometimes are even not enough to obtain good approximations like good emulators. I didn't mention that, but all of the problems, including the Skirm DFT one, you see a very rapid decay of the singular values. So in principle, you should be able to get very good accuracy. It's just that you cannot do it fast enough for it to be practical, at least in Mathematica for now. And the last thing is, I think a takeaway, at least for me, over the last few months, is that doing trade-off plots is very important so that we don't fool ourselves into thinking that we're making a lot of progress and it's actually just marginal progress. That's very important, at least to me. One last thing that I want to at least show you, because I just came from a collaboration meeting, a LIGO collaboration meeting in Chicago, and over there I even saw posters and stuff and met people that are actively working on reduced order models because of the LIGO calibration pipelines. Apparently there's quite a bit of expertise in the field over there, and I'm not extremely familiar with all the things that they're doing because, again, I'm a theoretical instrumentalist and I only do math as my night job. But I have talked to some of the grad students over there and some of the people over there, and they seem keen on trying to establish a connection with other places and see if there's any way to, exchange information so science can go faster. And that's it. Thank you very much. And I'll take some questions.
Very well, we have time for some questions. Jane.
Right. So usually the way that you choose it, you choose your parameters depends on your problem, depends on what are you trying to do. So for something like uncertainty quantification, you usually have a prior idea of what your nuclear interaction parameters are. And also, a lot of them are constrained by nuclear matter properties. So you know that from your knowledge of physics that some things are insane and some other things are more reasonable. And usually you try to set up your sample space from that reasonable choice. Again, that is very fudgy, is very...
Would it be better to sample two sets of parameters that are both in a very tight, reasonable range, or is it better one that's in the reasonable range and one that's...
Right. So I don't know if I'm following your question exactly, but let me try to see if I do it correctly. One thing you can do is if you have a parameter space that is a little bit wide in some sense, so that the models are not very efficient at reproducing everything, you could partition it into smaller places to have surrogate models that kind of work on smaller tesselets of the parameter space. And that's an idea that, you know, we haven't even explored in some of the particular cases we have, but then again, it introduces another fine-tuning variable that we have to have. And you know, we would rather stay away from having to put too many hands on trying to, like, we're gonna, you know, eventually you get to the point where it all becomes a lookup table, where every time you have parameters, you just have the values that you just evaluate. So yeah, that is right. Yeah, that is right.
also have like really
Right. Cal raises a very good point. So you sometimes can have greedy algorithms that can effectively sample the parameter space in a way that will be that would lead to a very efficient emulator on a blob around a central value that you start with. Yeah, I think
I'm going to go with Chuck, then Vitek, and then Morten.
So let's start.
Thank you.
Go back to the row to the alpha.
Yes.
The term functionals. Somehow the value for alpha that got chosen may be kind of sick. Creating problems for the functional that fits the average. And you may somehow be discovering that when it's giving you problems with this very nonlinear.
Right. So there's two things about that. I think just the fact that it's all nonlinear, even if the value of alpha is well behaved and the functions themselves are not changing very wildly, because we're moving too far away from the parameter that makes sense. The number of equations that you have in your coordinates grows exponentially. And so solving the equations just becomes extremely hard, even if you kept alpha fixed or varying on a very small narrow range. And yeah, sadly, that doesn't solve the problem.
Oh, but it's somehow a signature that the original problem has some deficiencies that the functional has issues.
In that sense, sorry for interrupting, it might be interesting to rethink the model. Maybe when people put that row to the alpha or those row squared times blah, 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 was to try to model some types of statistics, maybe we can try to aim at the same thing with something that is more amenable to this type of information. And that could be an interesting.
Yeah, I think that's something to think about. That's a very good point. Yeah.
Tree that we know that should be integer number if you really want to go to take that. But my comment was on the trade-off. Trade-off issue is absolutely important. Thanks for emphasizing the theories should never do calculations with accuracy methods needed, right?
Yeah.
But what is the accuracy which is needed, right? So you have your training set, which you have to calculate some training numbers using excellent model. You spend time to calculate some benchmark values.
Yeah.
And using this, you can get PSUQ.
Yeah.
Right.
Right.
Principal uncertainty quantification.
That's right.
Compared to the data. This gives you some idea.
Mm-hmm.
What is the accuracy which is
right?
That's
exactly right. Yes.
Yeah.
No, that's exactly right. And I think
that's the way to do it.
So what?
That's the way to do it.
I completely agree. Yeah, and this is the thing that I cannot agree more. And I don't think I can add much more to what you said. That's exactly right.
Thank you. Morten.
I think you have a pretty open.
Mm-hmm. Mm-hmm. Mm. Mm.
And that would actually catch.
Mm-hmm. Mm-hmm. Mm-hmm.
Different types of methods.
Right.
I think that, I come to know C9 don't have bonus.
Mhm.
It's a kind of behind.
Okay, yeah, no, that's a great suggestion. Yeah, I think we should look into that. Do we have anyone or ourselves with who went? Okay, your face up like, no, it's never gonna.
For the time-dependent DFT, which Edgar didn't show any of the plots.
That's right.
We are working together with friend Aaron here in implementing neural networks to try to capture that.
Yeah.
There we just gave up from the start. It's like,
Yeah.
no way.
Yeah.
right?
That is a thing, that thing of time dependent.
Yeah.
Excellent.
Oh, that's.
I mean, we get the same time dependent.
Mm.
And that's also kind of that would be issue.
Mhm.
Yeah. Yeah, and I think that's a very important thing that I feel like I want to also take out of this type of conversation is that we need to think critically, or I at least need to think critically about what type of approximator we're using to approximate the box. And a lot of times, these linear type models like the reduced basis method are very good for certain things, but at some point they just fall short, and you might want something a little bit more powerful because you need to reach deeper into your pocket. So autoencoders are something that a lot of the people that were doing these things in fluid dynamics have moved into as well. And I think there might be, I just want to leave it as a hint of like, there might be a reason for that. But I think it's exactly what you're saying. Yeah, that's right. That's right.
We need to eat, and I'm hungry. So we're going to thank Edgar one more time. If anybody wants to join us for lunch, more than happy to. He's going to stay here today and tomorrow. The schedule today is packed, but today we still have some slots if you want to meet and discuss with you. Thank you so much for coming.
Yeah, thank you for hosting me. Appreciate it. That's exactly what Bitex says. Exactly right. It's just put a benchmark.